Alright, fellas, the time has come that to now consider the second order corrections. Let's do it. I know you guys are eagerly excited for this, as am I. So let's do it. The easiest way to do this, I guess, is by brute force. Well, it's actually the only way to do this. So let's write it out. Again, our corrected state satisfies the following Schrodinger equation. H lambda n lambda is equal to E n lambda times n lambda. Okay, so now let's expand this guy out. H0 plus lambda delta H times n0 plus lambda n1 plus lambda squared n2 plus dot 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 equals En0 plus lambda En1 plus lambda squared En2 plus dot 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 times N0 plus lambda N1 plus lambda squared N2 plus dot dot dot. Okay, now let's look at the second order correction. Oh, that's way too bright. My bad. Let's pick orange. I like orange. Okay, lambda squared. That's kind of a weird orange, but maybe we can get something cooler. Okay, I don't know. Anyways, lambda squared. Let's look. We're gonna have H0 and this guy. That's one of them. We're gonna have En0 and this guy. Oops, sorry. Should have caught that. This guy, rather. Right? This is lambda squared. Anything else? Well, yes, lambda. That's lambda squared. Lambda. That's lambda squared. And also lambda squared and 0. Anyways, let's do it. So, I'm going to group this one on the left. H0 minus En0 times, what is it? This is all times N2, right? Equals, and then we're going to have En1, and then delta H, I'll swing over to the other side, delta H times N1, and then do I have anything else left? I have a En2 times N0. Okay, so this is it. And now what I want to do is I'm going to attack this from the left. I'm going to do the same thing that we did before. I'm going to attack it from the left with N0 first. And let's see what we get. So let me just write it out real quick. N0, H0 plus En0, N2. Now, at a certain point, this gets extremely laborious, but you just gotta go with the motions, you know? Just gotta go with the motions. And then plus N0, En2, N0. Alright, so let's see what we got here. Alright, first things first. This guy acting on that, what is that going to give us? Well, that's just going to give us En0 times N0. It's basically the same thing over and over again. You guys, if you practice this a bunch, you'll see that it gets much easier. So this guy is going to cancel with this guy, and this will be 0. And in fact, this will always be 0 when we attack it with N0. So 0 equals. Okay, now we look here. This guy is just a constant, and then we have N0 and 1. That's 0 because of orthogonality. And then we have this matrix element, negative N0 delta H, and then N1. Okay, and then this guy, En gets pushed outside, and this is just N0. N0 is 1 from normalization, plus En2. Okay, great. We have found the second order energy corrections. En2 is nothing more than N0 delta H and 1. Awesome. So now let's plug in N1. if you guys remember from before, n1 is simply negative sum m does not equal to n. What was it? Delta h mn over em0 minus en0. Let me slide this over a tiny bit, and then times m0. Okay, let me slide this over a bit more so you can see. So this is equal to, I'm just gonna slide out all the constants, negative m does not equal to n. Sorry about that. And then we have, let's see, we have delta h m n. And then look at this, we have this guy. Let me pick a different color here just to show you. We have this guy, and this guy, right? So that's going to give us actually delta h and m, right? Because it's just a matrix element between n and m. And then this whole thing is over em0 minus en0. And then since delta h is Hermitian, remember the Hamiltonian is Hermitian, so that this guy is the same as this guy because its complex conjugate is the same. So this is negative sum over m does not equal to n of delta h mn magnitude squared, right? Divided by em0 minus en0. And there it is, fellas. There it is. This is our second order energy correction. Nice. Nice. So now let's calculate the second order state correction. How do we do that? Same thing. But this time, instead of attacking it from the left with n0, we're going to do what we did before and attack it from the left with m0, where m does not equal to n, right? That's what we did before, so why not do it again? It gave us good results before. It'll give us good results now. Okay, so let me just write it out for you guys. It's going to give us it's going to give us m0, and then we have, if you remember from before, it's going to be, it's going to be h0 minus en0. And then this is all acting on n2, okay, and then equals m0, and then we're gonna have it's gonna be it's gonna be en1 first order energy minus delta h acting on n1 plus m0 en2 n0. Okay. What can we cancel here and what can we not cancel here? First things first. This guy acting on that, same thing as always, em0 and then m0. Okay, so the left-hand side is going to be em0 minus en0. And then the matrix element of the second order correction with the basis state. And then this guy, what is this going to give us? This is going to give us, let's see, en1, and then the matrix element m0 with n1, okay, minus m0 delta h n1, and then this term is going to be 0 because m0 and n0 are orthogonal, so we're just left with this guy. Oops, I forgot a parentheses again, my bad. Okay. So now I guess we have to plug in n1 here and there. Alright, this is going to get a bit tedious, but I guess we got to do it, right? I guess we got to do it. Alright, so let's rewrite this bad boy. I got my handy dandy notes here. Okay, so let's rewrite this real quick. We're going to have em0 minus en0 times m0 n2, second order correction, equals, Okay, now I'm gonna plug in n1. So this guy is gonna be negative en1, and then we're gonna have sum over, well now I can't use m because I already have m here. So let me use something else. Let me use something else. In fact, let me write this in a different color to make it a little bit more lucid. Okay, we're gonna have negative, and then this guy is gonna be en1, that stays, and then we're gonna have sum, and instead of m, I'm gonna say p, because we're summing over all the eigenstates. And if I write m, m refers to a particular one. So I don't want to get this confused. This is actually a very subtle point. This is a sum over all p. Okay? Where p can include m. Maybe, maybe not. Anyways, so this guy is just going to be delta h pn over ep0 minus en0 times p0. Right? Right. Okay. Sure. Oh, and I forgot the left-hand side. Left-hand side is m0. And then this is going to be p0. Similarly, for the second term, we'll do the same exact thing. Second term minus. This color coding scheme is pretty hard, I gotta admit. Sum p does not equal n delta h p n over ep0 minus en0. Okay, and then we're gonna have the matrix element m0 delta h, and then we're gonna have p0. Okay, all I did here, I plugged in n1. The red is n1. Now I have to plug in en1. I'm gonna have to use a different color for that one, aren't I? Okay, so this is equal to, and then we're gonna have negative sum over p does not equal to n delta h p n. And if you remember, the en1 is simply delta h n n. And then this whole thing divided by ep0 minus en0. And then we have the matrix element m0 p0. Okay, I like it a lot. And then minus, let me do it right here. Sum p does not equal to n, and then we're gonna have delta hpn. And what is this guy right here? This guy is nothing more than delta h mp, right? And then this is divided by ep0 minus en0. Okay, I like it. Now notice this guy right here. Let me get a different color for this. This guy right here. What is this? This is nothing more than delta mp, right? They're orthogonal and they are normalized. So basically this sum truncates to only when p equals m, right? So rewriting this, we get negative delta h. Instead of p, we're going to have m because of the Kronecker delta. So mn delta h nn over em0 minus en0, and anything left? Nope. Then minus sum p does not equal to n delta h pn delta h mp all over ep0 minus en0. Oh my god, we're almost there. Continuing, running out of colors already. Okay, so continuing, we can rewrite this as m0 n2 equals. So now we have to divide this whole thing by, where is it? We have to divide this whole thing by em minus en. Okay. So this is going to give us negative delta H M N delta H N N divided by EM0 minus EN0, and this thing actually is squared. Okay, let's see if I can fit this in. It's going to be a challenge. Minus sum over P does not equal to N delta HPN delta HMP over EM0 minus EN0 multiplied by, it's not going to fit. I'll just do it right here. EP0 minus EN0. Okay, so these are just the matrix elements. These are the projections that we were talking about before. So if we want to write the full state, we're going to need a lot of room here. It's going to be this. Okay, N2 is going to be, we include the identity, so let's sum over M does not equal to N. And we're going to have M0, M0, N2, right? This is just the identity. Same thing we did before. So let's look. What do we have here? Let's look. Okay, now we just plug it in. Plug and check. Negative sum M does not equal to N. Delta H Mn delta H Nn divided by EM0 minus EN0 all squared times M0. Okay, and then one more term, minus. Now we're going to have a double sum, right? The first sum is going to be over all M, and the second sum is going to be over all P. And this is going to be delta H P and delta H M P, right? Just from that guy on the right over there. All over EM0 minus EN0 times EP0 minus EN0. We did it. It wasn't that hard. It was just a lot of brute force, right? This is our second order energy. Corrected eigenstate. Energy eigenstate. Okay. And theoretically, you could just plug in all these matrix elements. You can plug in this, you can plug in that, you can plug in that, you can plug in that, and this is the second order energies. Okay, so we did it. We found the first order corrections to the energy in the state, and we found the second order corrections to energy state. If you're really ambitious, you can do the third order corrections. It's just going to be a lot more math, but you can do it. So next time we're going to do a nice example with the anharmonic oscillator, and we're going to see how everything comes together. Okay, so hope to see you then.